So in most cases, when we work with polynomial expressions, polynomials can be of any degree. They can be of degree 2, like we've been working with quadratic expressions, x squared plus bx plus c. But they can also be of a higher degree, as we've seen thus far. We can work with degrees of 3, 4, 5, 6, and in general, a degree of an infinite size, x to the 7th, etc. So when you look at these polynomials, consider factoring completely. In other words, anytime we have a polynomial expression, always consider if the polynomial expression has a common factor. In other words, look at each of the terms in the polynomial, understand the factorization for each term, and determine that if there is a common factor for each of the terms. So that'll be always our first step. Is there a common monomial factor? Is there a greatest common factor? From there, if there is, you will factor it out, leaving behind your resulting polynomial, for which you will then ask yourself the question, can I further factor this polynomial? So we'll take a look at an example here. Keep in mind that, of course, some polynomials may not be factorable, such as the one in the top right corner. Such factors are prime polynomials. So we have an example here, 4y to the 4th power plus 32y to the 3rd power plus 28y squared. We look at this trinomial here, we see it does have 3 terms. The first term, coefficient 4, exponent 4. The second term, coefficient 32, exponent 3. Third term, coefficient 28, exponent 2. So there are 4 factors of y, 3 factors of y, and 2 factors of y. How many are common for each of the terms? Because each term does have a y present, we see that the smallest exponent for the variable y is 2, indicating that there are 2 common factors of y for each term in the trinomial. Looking now at the coefficients 4, 32, and 28, we determine their prime factorization, and we look at which prime factors are common, giving us the idea of what our GCF for the coefficients would be. Well, notice here the numbers 4, 28, and 32 are all divisible by the number 4. 4 can divide into itself 1 time. 4 divides into the 28 7 times. 4 divides into the 32 8 times. So factoring out of 4 from the first term, you leave behind a coefficient of 1. Factoring a 4 out of the second term leaves a coefficient of 8. Factoring a 4 out of the third term leaves a coefficient of 28. And of course, if we also factor out the 2 factors of y, it gives us a greatest common factor of 4y squared. So we determine what we leave behind when factoring out the 4y squared. Well, the 4 goes away in the first term, and 2 factors of y are removed from the 4 factors of y, leaving behind 2 factors of y. In a similar fashion here, a 32, which is simply 4 times 8, well, that factor of 4 is getting removed, leaving behind the factor of 8. 2 factors of y are being removed, leaving behind 1 factor of y. And lastly, 28 is 4 times 7. The 4 is being removed. The 2 factors of y are being removed, leaving behind the simple term 7, the constant. We factored out our GCF of 4y squared, leaving behind a trinomial factor. Notice again, that trinomial, y squared plus 8y plus 7, is multiplying the GCF 4y squared, making that trinomial a factor. The question now becomes, can we also factor the trinomial that is also a factor? Y squared plus 8y plus 7, we have seen this one before. 2 numbers that multiply to give us 7 that will also add to give us 8. 7 and 1. 7 times 1 is 7. 7 plus 1 is 8. So our trinomial in parentheses can also be factored into the product of binomial factors y plus 1 and y plus 7. So our trinomial that we begin with ends up with the factors of 4, y squared, y plus 1, and y plus 7. If we multiply those all back together, we will get the original polynomial that we begin with. But what this allows us to do here now, it allows us to see what solutions we have to a function. If this was the function, if this was a polynomial function, then we would be able to see when our function was equal to 0. Simply by setting each of the factors equal to 0, y squared equal to 0, y plus 1 equal to 0, and y plus 7 equal to 0, we would be able to find 3 roots for our function. If y squared equals 0, then y equals 0. If y plus 1 equals 0, y equals negative 1. If y plus 7 equals 0, y equals negative 7. The values for y, 0, negative 1, and negative 7, if you plug each of those numbers individually, plug them into the original trinomial expression, then it will end up working out to equal 0. For example, negative 1 plugged into y to the 4th, negative 1 to the 4th is 1, times 4 is 4. Negative 1 cubed is negative 1, times 32 is negative 32. Negative 1 squared is 1, times 28 is positive 28. Therefore, 4 minus 32 is negative 28, plus 28 is 0. We were able to determine that simply by factoring the polynomial, setting it equal to 0, and solving for the variable. We will discuss in a later section the zero factor theorem that will allow us to do exactly that. We'll look at an example here, number 46. We have the trinomial 6x squared minus 24x minus 6, and we're being told to factor the trinomial completely. Anytime we look at a polynomial and we are being asked to factor, or if we want to understand what are the factors that make up our polynomial, we first look to determine if there is a greatest common factor. We will go to the full view. Before we do so, 6x squared minus 24x minus 6. Give you a moment to pause the video. And for each term, the 6x squared, the 24x, and the 6, we can use prime factorization. And then just by observing each of the prime factors that make up each of the 3 terms, we can come up with the greatest common factor. Keep in mind that each of these 3 terms here does not contain a variable factor. That last term, minus 6, does not have a variable, so we cannot factor out an x. The only thing we can hope to factor out is hopefully a real number that is multiplying the coefficients, 6, 24, and 6. Do we see a number that can divide into each of them? They're all even. 6, 24, and 6 are all even numbers, so we can at least factor out a 2. 6, 24, and 6 are all divisible by 3. 6 divided by 3 is 2. 24 divided by 3 is 8. And 6 divided by 3 is 2. What's neat, however, if a number is divisible by both 2 and 3, that means it's also divisible by 6, because 2 times 3 is 6. 6 divided by 6 is 1. 24 divided by 6 is 4. 6 divided by 6 is 1. So we go to the big board here. Noting that our greatest common factor is 6, we actually get a visual. Here we have it, 6x squared minus 24x minus 6, only we rewrote each term using factorization. We have a factor of 6 here because the 6 is multiplying the x squared to give us 6x squared. We have a factor of 6 here because the 6 is multiplying the 4x to give us 24x. We have a factor of 6 here because it's understood that 6 multiplies 1 at any time to get 6. So the 6 is common factor for each of the 3 terms. So it gets moved out front. When we factor, we introduce parentheses to determine what we leave behind. Well, let's see. If this 6 gets pulled out front, we leave behind an x squared. Minus sign. If this 6 gets pulled out front, we leave behind 4 times x, which is a 4x. A minus 6 times 1, well, if this 6 gets pulled out front, we leave behind minus 1. So right now we have the product of 6 and the trinomial x squared minus 4x minus 1. 6 is a factor. This trinomial is a factor. The question now becomes, can we further factor this trinomial? Because 6, yes, we could rewrite 6 if we would like to visualize it. 6 is 2 times 3. If you want to break it down and see each individual prime factor, you can write this as 2 times 3 on the outside. But we would normally simplify that using our arithmetic and just leave it as 6. Now the question here again, can we factor the trinomial? Looking at the trinomial, can we find two integers that multiply to give us -1 that will combine to give us -4? What are all the factors of -1? What will multiply to give us -1? This is the only pair of integers that will multiply to give us -1. Nothing else, right? If we try to change it to 1 times 1, that's 1. -1 multiply -1 is +1, not -1. Any other number such as 1/2 or 2 or 3 or 4, that's not going to multiply to give us a 1. 1 times -1. However, when you combine any number and its opposite, 1 and -1, 5 and -5, 20 and -20, they combine to give us 0. So if this was x squared minus 1, according to those special rules back in 5.4, 1 and -1 combine to give us the 0x, so x squared minus 1 would use these two integers. 1x minus 1x is 0x. 1 times -1 is -1. We get a minus 4x. So it turns out this right here is prime. That is a prime trinomial. That trinomial x squared minus 4x minus 1 cannot be factored into the product of two binomials. There is no greatest common factor here for these three terms. We already got rid of it. Our original trinomial had a GCF of 6. It gets factored out front. Our resulting trinomial cannot further be factored. So we're done. Our factorization here is the product of 6 and the trinomial x squared minus 4x minus 1. Center screen 47, x cubed minus 13x squared plus 30x. We are told to factor the trinomial. As we see here, we do have a trinomial of 3 terms, a 3-termed polynomial. Notice the largest exponent is a 3, x cubed, x to the 3rd power. So this is no longer a quadratic expression because we have a 3rd-degree polynomial. Remember, the largest exponent being 3 defines this to be a 3rd-degree polynomial. So this is understood to be a cubic expression or a cubic trinomial. For each of the terms, we see that we do have x to the 3rd, we have x squared, and we have 30 multiply x. The factor of x is present for each of the 3 terms. There are 3 factors of x in the first term, 2 factors of x in the second term, and only 1 factor of x in the third term. So we can only factor out 1 factor of x. Can we factor out anything else? The coefficient for the first term is a 1, so there is no other whole number that we can factor out. The 1 in front of the x cubed, the 13 and the 30, if you look at the greatest common factor between 1, 13, and 30, it's just 1. So we will simply factor out 1 factor of x. X cubed, but if you take away, keyword take away, subtract or take away, x cubed, factor out or take away a factor of x, you will only be left with 2 factors of x, therefore x squared. Minus 13x squared, if we take out a factor of x, we have minus 13x. And then the plus 30 times x, if we remove that factor of x, we leave behind plus 30. So we've factored out by our greatest common factor of x, leaving behind a trinomial. Notice here that if we move a factor of x, our trinomial that was cubic now becomes quadratic. It was a 3rd-degree trinomial, now it's a 2nd-degree trinomial times the variable x. For this trinomial, can we further factor it? In other words, can we find 2 integers that multiply to give us a positive 30 that will at the same time combine to give us a negative 13. Two numbers that multiply to give us positive but combine to give us negative, both numbers must be negative. And that's if we can factor it. We may not. Last example, we saw that you may not be able to factor a trinomial, and we've seen many examples in the past. Factors of 30, 1 times 30, but that will combine to give us negative 1 and negative 30 will combine to give us negative 31, not negative 13. Negative 2, negative 15, that multiplies to give us positive 30, but it combines to give us negative 17. Negative 3, multiply negative 10 is positive 30. Negative 3 combined with negative 10 is negative 13, which is what we want. So we'll write this out as what multiplies to give us x squared? X times x. What are the two integers we just found? Negative 3 and negative 10. These three prime factors, x is prime because we cannot further factor it. X minus 3 is prime because we cannot further factor it. X minus 10 is prime because we cannot further factor it. The product of these three factors will give us the trinomial x cubed minus 13x squared plus 30x, as we see here for number 47. Number 47 can be factored. We start with three terms, but those three terms were multiplied together somehow to give us these three terms. What did we multiply to get these three terms? We multiplied the x to the x minus 3 to the x minus 10. We can do that in any order we want. And I encourage you to try that out. Multiply this x to x minus 3, you get x squared minus 3x. We'll try this just one time. We could go ahead and multiply these two back together, and it would simplify to give us this trinomial. Distributing the x through to the trinomial, we would get our original third degree trinomial we begin with. What if, for example, we multiply this x to x minus 3, x squared minus 3x. Now we're going to multiply that to the remaining factor, x minus 10. This is just confirming that we will get back with what we started. A binomial times a binomial, we will use FOIL method. X squared times x is x cubed. X squared times a negative 10, negative 10x squared. Negative 3x times x, negative 3x squared. Negative 3x times negative 10, positive 30x. Combining our like terms, negative 10x squared and negative 3x squared, to get our minus 13x squared, and writing out the rest of our terms. So it confirms here that our factorization of x times x minus 3 times x minus 10, that is our correct factorization there. Looking at number 50, 4x cubed plus 8x squared minus 12x. Factor the trinomial completely. Very similar to the previous example in that each of the three terms has the common x factor. So we see that we can factor out at least one factor of x, but can we factor out anything else? Looking at the coefficients, 4, 8, and 12, maybe as we count that, right, 4, 8, 12, what pattern was that? 4, 8, 12, well, that's a multiple of 4, which means the numbers 4, 8, and 12 all share a common factor of 4. We'll go to the big board here. The way that we can think about this, the way that we could visualize, 4x cubed, right? X cubed just means we have three factors of x. 4x cubed plus 8x squared minus 12x. That's the trinomial we're working with. We want to factor the trinomial. In order to factor the trinomial, we have to be able to visualize. We have to be able to see the factors that make up our terms. Now, can we determine factors that are common for each of the three terms? I see a 4 here, here, and here. So there is a factor of 4 that is common for each of the three terms. Are there any other factors? There is an additional factor of x that is also common. So both the factor 4 and x will be factored out, telling us that the greatest common factor is simply the product of the common factors. So our greatest common factor is the term or the expression or the monomial 4x. 4x gets factored out front, we always introduce the set of parentheses to determine what we leave behind. Well, now that we actually have it visualized, we can see 4x cubed with the 4x pulled out, we leave behind 2 factors of x, which is x squared. Bring down the plus sign. The 4 and the x factored out leaves behind a factor of 2 and x, which is 2 times x, which is 2x. Minus sign. The 4 and x go out, leaving behind the 3. The product of 4x and the trinomial x squared plus 2x minus 3. We now focus on the trinomial, determining whether or not we can factor it. Can we find 2 integers that multiply to give us negative 3 that will add to give us positive 2? 3 is a prime number. 3 times 1, those are the only 2 numbers or integers that we can multiply to give us 3. But for negative 3, we have negative 1 and 3. We have negative 3 and 1. Which of those 2 pairings would allow us to combine to get positive 2? 3 multiply negative 1 is negative 3. 3x minus 1x, right, using these 2 integers here as coefficients, 3x minus 1x will combine to give us 2x. So these are the 2 integers that we want. So here, our x squared plus 2x minus 3 will factor into the binomial product using these integers, positive 3 and negative 1, x plus 3 times x minus 1. And of course, this factor here, these 2 factors, are being multiplied by the GCF of 4x. So 4x cubed plus 8x squared minus 12x. Our example here for number 50. 4x cubed plus 8x squared minus 12x. We factor out the GCF of 4x. 4x gets moved out front. The remaining trinomial that we leave behind can also be factored into the product of 2 binomials, x plus 3 and x minus 1. 3 and negative 1 were the 2 numbers we found that would combine as coefficients to give us 2x, that would multiply as integers to give us negative 3. So we place them into our binomial product for x plus 3 times x minus 1. Looking at the number 58, negative 5x squared z plus 15xz plus 50z. Give you a moment to pause the video and take a look at that, noting that each of the coefficients there end in a 5 or 0, meaning that it is divisible by 5. You can count 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So we can factor out a 5. Also, we see that each of the terms has the variable z. The z can be factored out along with the 5. And also see there that the first term, the leading coefficient, is negative. So we would also want to factor out the negative sign. So our greatest common factor here, the factor that we will factor out, is negative 5 times z. If we factor negative 5z out of the first term, we can see that we leave behind x squared. Negative 5z factored out of the first term leaves behind x squared. Take a moment to see what else we get for our second and third terms when we factor out negative 5z. Pause the video. We'll go to the full view here. When factoring out negative 5z, you will see that we leave behind x squared minus 3x minus 10. The negative 5z, when multiplied back to negative 3x, negative 5 times negative 3 is positive 15 with the additional xz factors, and you see that matches up with the second term. Negative 5 times negative 10 is positive 50 with our factor of z plus 50z as it matches up. So we did correctly factor, leaving behind the correct trinomial factor. Now the question is, can we factor this trinomial? Two numbers that multiply to give us negative 10 that will add to give us negative 3. If we can find them, then we can factor it. 1 times 10 got to be negative, so negative 1 times 10, 1 times negative 10. Neither of those combine to give us negative 3. 2 times 5, but it's negative, so negative 2 times 5, 2 times negative 5. Which of those combine to give us negative 3? It's positive 2 and negative 5. A positive 2 multiplied negative 5 is negative 10. A positive 2x and a negative 5x will combine to give us the middle term, negative 3x. And of course, we see that x times x will give us the x squared. So that's where our 4 steps come into play for the FOIL method. We are trying to factor the trinomial, we are reversing the FOIL steps. The 2 integers that we get here that multiply to give us negative 10, those integers are coefficients that will combine together for our variable term, negative 3x. Positive 2x, negative 5x combine to give negative 3x. So our binomial factors here, using our variables x and our integers 2 and negative 5, for a successful factorization, negative 5, z, x plus 2, and x minus 5. I again encourage you, FOIL these two, distribute these and multiply and simplify. Distribute the negative 5z and see if you end up with the original expression we begin with. You, of course, can also begin by factoring the negative or distributing the negative 5z into x plus 2, and you will have a binomial. That binomial you then can multiply to x minus 5, and by combining like terms, you will be able to show that you have the original trinomial.